Okay, chapter 4, Volcanoes. One of the reasons I kind of wanted to show this picture, I know there's a lot of fantastic pictures of volcanoes, around the internet, and just fantastic photography and videos and things. This is when I was flying into Seattle, and I snapped a quick picture out the airplane window, and I was flying into Seattle. So I was flying from Arkansas to Seattle or Chicago or wherever it was, but into Seattle, and I noticed something. These here are volcanoes, and this is Mount St Helens, and then Mount Adams and Mount Hood. I forget which is which. But what you're looking at is kind of a really neat feature, and it's kind of this global, I don't know, huge feature that you can't easily see anywhere from the surface of the Earth. But what's going on here is we talked a little bit about plate tectonics, right? You've got the ocean that's out here, and there's the oceanic plate that's actually subducting underneath this continent, and it's melting. And as it melts, it's coming back up and creating these volcanoes. And so you're essentially looking down this line to the south from Washington into Oregon, where you can see these volcanoes popping up from this subducting oceanic plate. So you're sort of looking at the result of plate tectonics. So I just think that's kind of neat, and I kind of wanted to share that. So what are we going to cover? So first off, we're going to talk about what are extrusive rocks. In the last chapter, we talked about intrusive igneous rocks, and now we're going to talk about extrusive igneous rocks, which is basically volcanoes, the effects of these volcanoes on humans, the different types of, not necessarily violence, because I mean we'll talk about volcanic hazards down here, but I want to talk about the relative violence of volcanoes, why some are more explosive and deadly than others really quick. And then we'll get into well, we won't get into classification identification. I'll actually cover this in class. And then I want to talk about the different types of shield volcanoes. So first off, extrusive igneous rocks, and then there's intrusive down here. So we talked about these intrusive ones before, where you cool off a magma inside the earth, and it takes a long time for this to cool off, just because it's so insulated from the material around it. And when you take a long time to cool those rocks off, you can get little crystals forming in here and see the minerals. And so that's why when you look at a piece of granite, you can actually see the individual minerals in there. You can see the feldspars, you can see the quartz, biotite, etc. Extrusive igneous rocks are stuff that erupts out on the surface. So the magma makes it to the surface as lava and can erupt. There's a variety of different ways it can do that and different types of chemistry that will result in different types of rocks, which we'll look at in class. But if it gets to the surface, we call it an extrusive igneous rock, which is basically a volcanic rock. So here we have an example of that. This is the big island of Hawaii. And what you see here is all these extrusive igneous rocks. And this is something I want to kind of hit on, and I'll talk about it in the class, but it's something you can definitely hear more than once. We classify igneous rocks not just based on whether they're extrusive or intrusive, but also based on their chemistry. And basically it has to do with the SiO2 that's in it, the silica that's in it. I've talked about silica before. I'm going to talk about it here in a minute. But rocks that form over oceanic crust are more mafic. I wonder if I can spell that. Mafic, which means there's less silica in them, and they are inherently just darker. They'll have heavier elements in there. They'll have iron and magnesium, and so this stuff right all around here is mafic. It's called basalt. It's a black extrusive rock, and we call this stuff mafic. So this is what you'll find out on oceanic plates of a lot of volcanic islands. However, the continents are underlain by silica, right? The continents are basically granite. It's all feldspar and quartz underneath our feet if you go down deep enough. And that stuff is actually called felsic. And there's no felsic rocks anywhere on this picture, but I'll still just spell that too. Felsic. Whatever. You get the point. And felsic stuff is lighter colored, it's lighter elements, and it's primarily silica, or stuff that has a lot more silica in it. So let's talk about the effects of volcanoes on humans. For one, they're very explosive and deadly, and they can kill you. Right? It's bad news. That's one of the main effects on humans, and that's a big reason why we pay attention to them. Plus, they're just awesome feat of nature that exists here on Earth and elsewhere. But number one, they're deadly. Number two, we tend to live near them in a lot of cases. The material that comes out of volcanoes can be really beneficial to farming. We tend to vacation there when they're in tropical areas. This is Oahu in Hawaii. I actually used to live in that little apartment right there. But not only are these places, fun to live on or good for farming. I mean, even historically, right? If you're a fan of the Moana movie, the Polynesians voyaged and colonized throughout the Pacific, and they hopped from these volcanic islands one to the next, and they were able to sort of successfully create civilization there, and that was important. On top of that, you want to get into kind of more modern history. Talk about World War II. Pearl Harbor is just off this image over to this way. If you're a World War II buff, you understand that these volcanic islands played a huge part in the logistics of that war and what happened in that war. So, volcanoes. Along those lines, this is also in Hawaii. This is actually on the Big Island. I just think this is a cool thing, and I love to show it. There used to be a volcano here, and you're kind of down in the guts of it. So the volcano used to sort of be, up here somewhere, and over time it has eroded down just due to erosion, weathering and erosion, which we'll talk about later. But you can kind of still see the remnants of that crater. But what's really neat about this is this material in and around here, all this green stuff. And you've seen this mineral. This is a green sand beach, and this is olivine. So if you remember those pieces of olivine in your box, and hopefully I showed you guys pictures of olivine that's actually kind of pretty. This olivine is prettier than what's in your box. It's a deeper green. And if you remember olivine, or if I haven't mentioned it yet, it's the gemstone version. So if you take a piece of olivine and cut it to where it looks like a nice gemstone, is peridot, which is the birthstone for, I think, August. Is peridot the birthstone for August? Okay, we're not sure. I had to ask another geologist, and we're not sure. But I think it's August. So if your birthday's in August, but go ahead and check. Maybe October, maybe September. So yeah, kind of a neat thing to kind of go hike out here, and you can hike around this this gemstone beach. It's one of the few places in the world you can do that. It's pretty wild. Another example of a sort of a volcanic island. Now, not every one of these little peaks here are volcanoes. And more than likely what used to exist is you used to have kind of a larger volcano that was here, and weathering and erosion has kind of taken it down to where you can have these smaller mountains around here. But what's going on here is it's called Unalaska, and this is actually sort of a famous harbor called Dutch Harbor. So if you're a fan of the Deadliest Catch series, this is where the majority of that fishing fleet resides. So thanks to these volcanic islands, they can be closer to the Bering Sea, which is heavy and crab, right? You go out there and you catch crab. So a lot of the crab you eat actually comes out or is fished from this port and is fished out here towards the Bering Sea, and is brought in here. But yeah, so more volcanic islands. Another thing that they're useful for is geothermal energy. So I believe this is in Iceland, and a little bit later we'll talk about shield volcanoes. And this is a fantastic looking shield volcano right there. But there's heat closer to the surface on these volcanic islands, which is not a big surprise. But what you do with this geothermal energy is you can kind of drill down in the ground where it's hotter. You send water down there, it gets hot, it comes back up, and you can drive a turbine. Essentially, it's a little more complicated than that, but that's basically how it works. And you can generate energy from this, and it's basically, I don't want to say it's free energy, but it's quite efficient once you kind of build these places. the upkeep of them is not that much, and you're generating energy from heat that's already there. So kind of a neat thing. I know, kind of a morbid picture, but this is Pompeii in Italy. And if you've never heard of this, what happened is during the Roman era, Mount Vesuvius erupted, and you had this huge pyroclastic flow, which we'll talk about in a minute. We had this huge pyroclastic flow. It came down and kind of obliterated this town, but it also preserved a lot of the people and a lot of the things in this town. And without that volcanic eruption, we wouldn't have had this kind of preservation. So we've learned a lot about how the people in Rome, at least especially in this town of Pompeii, how they lived their lives. And so it taught us a lot about history thanks to this volcano sort of preserving this. As terrible as this event would have been, it's still quite amazing that you can get so much knowledge preserved and so much information preserved over time thanks to this terrible and very violent but volcanic eruption. One of the things that volcanoes will do is they will cause climate change. When we talk about climate change today, and we definitely will talk about climate change, it's one of the last things we'll talk about in the semester. And typically we'll talk more about global warming, what's happening today. But volcanoes will actually cause global cooling, at least on the short term. And the reason they do that is they'll throw up a lot of sulfates in this. Most of what you see here is actually steam. It's mostly water that comes out of these volcanoes. But they also throw up a lot of sulfates. And that will act as sort of a cooling agent in the atmosphere. It'll block a lot of the radiation coming from the sun. And if you get a volcanic eruption large enough, you can really affect the Earth's climate for at least a couple of years. And I really mean that, like 1, 2, 3 years. The last time that the United States, I believe, had a famine was in 1815, if I remember. I'm not going to test you on this. The fact that I can't even remember it off the top of my head. And there was this huge volcanic eruption in the southern hemisphere, and it threw up so much material that it caused what was called the year without a summer. And basically it was snowing in July in parts of the United States, not just the high peaks of the mountains, but it lived up to its name, the year without a summer. A lot of farms failed that year, and it was a famine in the United States. And this is something we really haven't seen in modern history. If we had another volcanic eruption like that, it would be quite a big problem for modern society. So another reason to really pay attention to volcanoes. So, violence and silica. So I've talked about silica before. It's SiO2. It's basically quartz, but it's not just quartz. We've talked about feldspars, which some of them have aluminum in them, some of them have sodium in them, some of them have potassium in them, and then after these you'll end up seeing the SiO2. So we'll call them aluminosilicates and potassium silicates and sodium silicates, and these are the different feldspars. So if you remember from that last chapter, I kind of started out talking about the rock-forming minerals, and you see that majority of the Earth's crust are feldspars and quartz. Well, this is what it is. It's SiO2 and this other stuff. And how much silica, how much of this stuff is in a magma can determine how explosive and violent it will be. So places like oceanic crust, like Hawaii, for instance, there's not as much silica in the magma. There's still a lot of silica. It's still mostly silica, or at least about half silica, but it's nowhere near like 100% or 90%. And because of that, you get these oozing, flowing lavas that come out of Hawaii versus the continents, where if you have a volcano coming up through a continent, it is mostly SiO2 for certain. And SiO2 creates these really sticky chains. And so when that magma comes up, once it reaches the surface and it has a place to go, boom, it explodes. Versus in Hawaii, it's just not under as much pressure. It's not as sticky because of that silica, and it'll just kind of ooze and flow out, and it's not nearly as deadly. Although you put your house in the path of this stuff, and it's no bueno. But Anyway, so that's kind of what goes on, why some volcanoes are more explosive than others. And that's kind of the base. It's a little more complicated than that. A lot of it also has to do with how much water content is in here, but for the most part, it's this stuff. The more SiO2, the more violent it is. And that's the reason we see more violent volcanoes on continents, is they're coming up through a granite continent. The continents are mostly silica, and basically the way I think of the continents is they're kind of like a glass of water. So imagine a glass of water. Imagine the Earth is a glass of water, and you've got ice cubes in that water. The ice cubes are floating on the surface, right? And you can't really push them back down into the water. They just float because they're less dense. The continents are basically the same thing. They're made out of mostly this silica material. Silica is just a light compound. It's not very dense. And so the continents are like these ice cube-like rocks that just float around on the surface of the planet, and they're just not really going to get subducted back into the planet from plate tectonics. They're just too light. But they also happen to be rather sticky if you melt this material, and so you get explosive volcanoes. And I'll hit you guys again with that in class. But really, that's kind of an important aspect of these igneous rocks. You know, if you didn't catch all that, rewind this video, listen to that again. It's important. You get explode. You know, I may ask the question, why do we have more explosive volcanoes on continents versus oceanic crust? You know, continental crust versus oceanic crust. So remember that. So yeah, high silica content, low silica. Something I kind of grew up with. So I was born in 1983. And so when I was in elementary school, it was the late 80s. And all the time in science class, every year in elementary school, we'd watch a documentary on Mount St. Helens. And I'm sure we'd watch like the same one every year. But Mount St. Helens was the largest volcanic eruption on U.S. soil in the United States' history. That's not saying we haven't had larger volcanic eruptions in North America in time, right? I mean, there have been larger volcanic eruptions. You know, Yellowstone comes to mind. But in the United States history of the last 240 million years, or 240-ish years, not million, 240-ish years, or however old the country is, this was the largest eruption. And it was fairly catastrophic. It did a lot of damage. The fallout of the ash, so when this cloud really kind of kicked up ash into the atmosphere, it carried for hundreds of miles away. And I don't need to tell you this whole thing because I'm going to post this video on Canvas, and you guys can go watch that. So go watch that, and then come back and actually don't come back to this video. This will be the end of this video. Go to the next one and continue watching on from part 2. But I want you to go watch this few-minute video that kind of talks about Mount St. Helens, and you can understand what happened with that.